Hello, everyone. Welcome to today's webinar on optimizing contamination control series and in-depth look at filtration. My name is Heather Bersillo, and I will be hosting the webinar today while Evan Zabowski will be presenting. If you do have any questions at all during the webinar, please go ahead and put them in the questions section of the GoToWebinar menu, and Evan will have time at the end of his presentation to answer most of the questions. If we don't have a chance to get to your question today, we will be able to email you after the fact, and we will also be providing a recording of this webinar to everyone that's attending today. And with that, I'd like to introduce Evan. I'm sure many of you know him. He is an authority in the industry, but Evan has been with Testoil for many years now at this point, and he trains our customers in a variety of fields, including lubrication fundamentals, contamination control, condition monitoring, RCM, FMEA, and used oil analysis. Training is often geared towards the CLS and OMA1 certifications from STLE, as well as the MLA and MLT certifications from ICML. Evan himself is a certified lubrication specialist who also holds certifications for OMA1, MLT1, and MLA2. And his many professional achievements include significant contributions to STLE, such as being named the editor of TLT, the Society's magazine, in 2009, and he had served in that capacity for many years. He's also been nominated to STLE's prestigious board of directors. Evan has been a key member of STLE now for over 20 years and donates his time to serve as the chair of the Alberta, Canada section, and also as an instructor of the condition monitoring courses at the STLE annual meetings. He has served as the editor of STLE Alberta section's Basic Handbook of Lubrication, the 3rd edition, which I believe many of us have used and read over the years, as well as a couple other publications. At Testoil, Evan's objective is to offer remarkable assistance in every possible way in order to ensure that our customers are satisfied. And to that end, Evan leverages his outstanding industry credentials every day with the people that we work with. So without further ado, Evan, I will allow you to take it away.
Great, thanks, Heather. So yes, this is part of the Optimizing Contamination Control series. The series began by going through essentially 5 steps. And the first step was taking delivery of the oil. And with that step, our big goal was understanding why new oil was not necessarily clean oil and how to set a target cleanliness for how clean it should be. That covered the first webinar in the series here. But then the second webinar went through 2 further steps, one dealing with storage of lubricants. So once we've taken delivery of them, how do we store them in ways that we don't encourage contamination and maybe even take steps to reduce some of that contamination? Kind of the same thought goes with the handling steps and how do we take it out of storage, get it to the machines in a way that, again, doesn't encourage contamination, and probably now we at least have some opportunity to reduce contamination. So the other 2 steps that we're going to cover today, we're going to go through exclusion. Essentially, we'll discuss breathers and why OEM breathers are often inadequate and what we need to do to improve them so that we can keep dirt out of the system. And then the last step, we will discuss filtration as it applies to one of the various forms of conditioning the lubricant. So at this step here, we will finally be able to address any concerns regarding meeting the target cleanliness that was set in the very first step if we haven't yet already achieved it, because not everyone can or has the ability to filter their oils in storage or during handling. But once it's in the machine, this is our last chance, our last gasp at hitting that target cleanliness and promoting longevity to the equipment's life. So let's begin with step 4 here, the exclusion step. We'll discuss breathers. Why do we have to discuss breathers? It's because, honestly speaking, most OEM breathers do not meet reasonable criteria for exclusion. With that, any breather that is installed often has, subpar performance. But when there isn't a breather, then we're counting on everything else helping, and that includes fill caps being tight and in place, dipsticks not being popped out due to pressure, any inspection covers or hatches also closed and sealed properly. Without all these working together, a breather won't, in essence, breathe. Air finds the path of least resistance, so air will go through whatever path it can find. So we need to understand what we have when we have a breather. And often what you see is various quotes out there that basically just reiterate the ounce of prevention is worth a pound of cure, that it's easier and therefore less expensive to exclude the contaminants and keep them away from your systems than it is to try and deal with them after the fact, after they've gotten in. And so there's been a variety of quotes out there over the years. I've reproduced one here that tried to set the record a little bit straight, because often people use a 10 times quote. And this article I'm quoting from admitted that it's not always 10 times, but it's got to be in that neighborhood, that it at least is significantly cheaper to buy a breather than it is to bring in a filter cart, right? So like I said, an ounce of prevention is worth a pound of cure. But when I make the comment that OEM breathers are often inadequate, I give you two examples right here. The top one is your standard, what we call quarter turn breather, because the cap takes all of a quarter of a turn to remove it. You can see that there's a basket that goes inside the collar that attaches to the piece of equipment, the tank, the reservoir, whatever it happens to be. And many times, those of us who are out there in the field will see that these screens are either completely missing or sometimes, in fact, damaged. And on occasion, they may even be purposely damaged, where people jam a screwdriver into them, poke a couple of holes just so they can pour oil in faster. But the ultimate protection comes from the cap portion of these breathers. And if you look inside the cap, you're going to see one of two things. Either nothing, it's just an empty void, or at best, typically we see some form of steel or brass wool. That wool does not really stop a whole lot. It doesn't stop any of the fine particulate, any of the clearance-sized particles that we talked about in step one, and it certainly does not stop or in any way reduce moisture. Jokingly, I refer to these type of breathers as dead animal filters, because my logic is they only stop mice from crawling in and dying. So they're not really good exclusion devices. The other form is what's usually referred to as a gooseneck or a snorkel. It's a 180-degree turn of pipe. These things are often found on very large outdoor applications, and it's simply a way of preventing rain from getting in. But I've seen them certainly in indoor applications. I've seen smaller versions of them. I've seen birds' nests inside these things. I mean, they're just wide open pipe leading into the system, and sometimes they have a piece of screen on them to stop birds from nesting in them. But again, they don't stop a lot of dirt, and they certainly do not stop humidity. They may stop rain, but they're not going to stop it breathing humid air. So we need to look at better designs for breathers. And really, there's a whole host out there, but the most common type many of us are familiar with might look something along the lines of this one here. Often they have desiccant as part of them. So they're a two-part breather. One part is for the particulate, and another part is for any moisture. The nice thing is that the particulate side of them can be high enough quality of filter that it will filter down to about 1 micron, which is pretty much small enough to exclude all airborne particulate other than smoke. The desiccant portion of it is there to remove any of the humidity in the air, and they're pretty efficient as long as they're changed regularly. And that's kind of what I'm leading into for my next point, is that when we install these breathers, we often install either a disposable version or a rebuildable version, like the one I'm showing here. And you need to know when to change them, when they are spent, when they are consumed. And the particulate side of them can last a significantly long period of time, but the desiccant side may have a much shorter life depending on the humidity in the area. So a great question to ask yourself is, how do you know when they're spent? And a better way of phrasing that question is, in what direction does the color change? And often people think of the answer a bit too literally in terms of the color rather than the word direction, and they just assume they change from blue to pink or something like that. Point is that you should know the proper operation of your breather and what that color might look like. So I'll give you a couple examples here that, yes, one of the more common brands, Desiccant, does change color from blue to pink, but it's more important we understand the literal term direction. What direction is it supposed to change in? And the air is breathed in through the bottom of the breather up to the top and then down through the center. That's how a tank or reservoir will take a breath in. And that's when the desiccant breather should be doing its job. It's stopping the humidity during that breath in. So the color change should be from the bottom towards the top. And I mentioned the color because there are different brands out there. I'm showing you a different brand here that's got red and yellow as the colors that it can change. So we need to understand what breather we're using, know the color that it should be, and understand the flow direction within that breather. And like I said, this is a very common style to breathe through the bottom into the top. And the most common version of it, or at least brand of it, changes color from blue to pink. There are other brands though, and this raises a different question because the construction is a little bit different, but they get into the top first and then down through the desiccant into the tank. So the color change in these should actually be from top to bottom. And as you can see, the color starts off at kind of a yellowy orange color and then changes to a dark green. So I always encourage people who are purchasing breather technologies when they go for the desiccant style to purchase them all from one supplier. My point is that you need to get into the habit of knowing what direction the color changes and what the color change looks like. If you took a brand new desk case, which would be essentially kind of a medium to dark blue, and compared it to an absolutely spent air sentry that I'm showing you here, which would be a dark green, and put them out under, say plant lighting conditions or a darkened area of a facility, it could be easy to mistake completely spent air sentry for a brand new desk case, and you would think the breathers were fine. So make sure we know what color they're supposed to be. Don't mix brands so that you get different colors, but most importantly, don't mix styles in terms of flow direction. It's not to say that any one design is better than the other for the ability to remove humidity, but just your ability to go around and do self-checks on your systems. I'll show you an example of a customer of ours that was using an air sentry. If you look closely at this picture, you can see that breather's towards the back of the picture. And if you're looking near the bottom of it, you might be able to detect that it started to change color at the bottom. So this is why it's important to know the proper direction of color change, because this one was changing color in the wrong direction. So it doesn't mean that it was, putting water in the oil, of course. What it means is the water was already in the system. So every time this thing took a breath out, it was pushing water into the desiccant breather and trapping it, which is, a bit silly because really you want the water out anyways. Why would you bother trapping it on the way out? It's kind of like, trapping mice after they've chewed the wires inside your house. It might give you a small sense of satisfaction that you've done it, but you didn't stop the damage from happening. So this customer recognized that the breather was changing color in the wrong direction and therefore needed to take some different sort of tack on this. So here's where things get a bit silly. They got out, you can maybe make it out there on the left-hand side of the picture, a calibrated coffee cup, and they propped the tank lid open. The logic being, if the water wanted out so desperately, let it out. Well, think of this from the water's perspective. If you're the water and it's hot enough to turn you into a vapor and you're willing to leave the surface of the fluid, and now that somebody's left the tank lid open, where do you go? Well, hopefully you recognize that you will simply rise from the level of the fluid, and once you get into the airspace, all you're going to do is go straight up, hit the tank lid, condense, and fall right back in. This fix was not effective, and if anything, it allowed more dirt to get in the whole time. So this is why we check the operation of our breathers, make sure they're changing color in the right direction, because ultimately we can learn that maybe our water issue isn't environmental, it isn't humidity like this example here, and we need to look at other means of removing the water. We should also, of course, then look for what that source is, because obviously it's something internal, probably a chiller or a cooler. But other things to check regarding the color is, what if it changes the color it shouldn't? Most common color that they can change is usually a dark color, something near black, and that just means oil has contaminated the desiccant. When this happens, the desiccant no longer functions. So you've lost your ability to remove water, for one, but two, it tells you you're getting oil in places you typically shouldn't. Now, this may be for a variety of reasons. One of the worst ones would be if it was actually foaming, but sometimes it could just be a collection of oil vapors because the system runs hot enough. Or if this is on a mobile piece of equipment, it could just be sloshing from the oil moving back and forth within the machine. But in any of those three cases, one of the easiest solutions isn't to put a standpipe and simply raise the desiccant up out of the way. The better solution is to use one of these little adapters, and essentially they've got a double duckbill flap in there. It just is a tortuous path. It helps collapse the foam, condense the oil vapors, and prevents sloshing from getting up in there. You don't have to replace these when you replace your desiccant breathers. They're a permanent installation. On occasion, you may need to remove them and clean them, but that's fairly rare. But the point is they protect the breather. So you're not throwing away good money simply because you allowed your brand new breather to get coated in oil. So with that, remember, a breather is meant to breathe. And just because we install a breather does not mean it's breathing through the breather. If you take a close look at this picture here, it's one of many I've seen over the years where people have installed a breather and then left another door open somewhere else. And this one was literally the door. It's the tank lid. And if you look towards the left-hand side of the picture, hopefully you can see what I was trying to capture in the picture, and that I can see daylight all the way through the top of that tank lid. Now, when I come across situations like this, I'm often, kind of in a jovial mood with the people that are touring me around, and I'll look at that breather, look at the tank lid, and I'll say to them, that breather is going to last forever. And I'm being sarcastic because I'm saying there's no way that that breather is going to breathe, so therefore the desiccant will never be consumed. And they don't catch that I'm being sarcastic. They think, oh, great, that's awesome. I'm like, no, it's because it's not working. So many times I've seen breathers installed in such a way that there's somewhere else the air will breathe. So it could be those quarter turn breathers are left installed. It could be that there's more than one point of entry into the tank, right? And they haven't all been plugged up. And more times than not, it's because seals have either been compromised, thrown away, damaged, whatever it is. And if we don't have the system completely sealed in every other spot, air will not breathe through the breather. So simply installing one doesn't actually get you all of the effects you're hoping for. So that's kind of the big thing that I'm always going for when I recommend improvements to systems. It's not just an aspect of buying the right tools, right? That's one of the things we always say, that it doesn't matter how many of the right tools you have. If you don't know how to use them, they're never going to work. So keep this in mind when you're looking at installing breathers. So with that, I'd like to share just a couple more stupid stories that I've seen over the years, because hey, why not? We should enjoy this. This picture here was from a potash mill I had visited, and I was going around doing my audit, making notes that many of the pieces of equipment needed a breather. And lo and behold, I did notice one that actually had a breather on it. So, eyes locked across the room, Dreamweaver started playing in the background, who knows? But I go over to this piece of equipment because I'd like to take a picture to document this is done the right way. And as I'm getting closer, I noticed something, and it was that all the little red plugs were in the bottom of the breather. Now, I couldn't see the whole breather. All I could see was the one side. So I was giving it benefit of the doubt, because those of us who've been in industry a long time know that when these breathers first hit the market, one of the instructions was relating to the flow rate through the breather, that we would remove only a certain number of plugs. And the way you do the calculation, which I didn't reference at that point when you saw it on the slide earlier, is you take the gallons per minute flow rate that you have for oil, divide by 7.5, and that'll give you cubic feet per minute of air exchange. With the cubic feet per minute rating, you would say, okay, this is my rating. You'd look it up compared to the breather you have. It would tell you to remove 2 plugs, 3 plugs, 4 plugs, however many it was. And people would do this. And therefore, thinking they were maximizing the performance of the breather, after a few months, they'd pull out a few more plugs. And I don't know, the mentality was simply that if you only used a few of the plugs, that you were basically holding some of the breather in reserve, and then you could remove later plugs and get more of the capacity later. Not exactly true, but it was a thought, I guess. So it was common in industry when these things first hit, like I said, that people only removed some of the plugs. So as I walk up and I see all the plugs on the one side, I'm assuming, that benefit of the doubt, the plugs on the other side have been removed. Well, hopefully what you can get from the way I took this picture, because I tried to get underneath and show, no, the entire ring of plugs is intact and in place. And the funny part of the story is that having taken this picture, when I finished up for the day, I met with the reliability manager and I showed him this picture. And, just with a smirk, and you got your camera in your hand, you're like, look at this. Like, who does this kind of thing, right? You're thinking like you're trying to make light of a bad situation. And the reliability guy takes one look at that picture, deadpan, hands me back my camera and says, at least they took the plastic off this time. So yes, it's true. You do have to remove the shrink wrap. You do have to remove the plugs. Standard practice now in industry is just to remove all the plugs. They don't tell you to remove only part of them. They just say tear the entire ring rate off and away you go. There's no point trying to choke the flow of air into a breather. You just let it breathe as it wants to breathe. So with these things, like I said, you do have to take the right measures when you install them. Seal everywhere that isn't a point of entry that you don't want air going through. So fill caps, dipsticks, inspection covers, hatches, all of those count. Make sure the air is actually going through the breather. To do that, remove the shrink wrap, take the plugs out. It just seems like silly things you have to mention, but I've seen it more than once where breathers have been installed in such a way that effectively they're not going to breathe. So with that, we've done the step 4. We should move on to step 5 now, filtration. This is the big part of the presentation, usually the most important part. What we need to understand about this step here is we're reverting all the way back to that target cleanliness we set in step 1. We need to now achieve this cleanliness. So if we have not yet taken any steps to improve the cleanliness of the oil, then we know for sure it is still not meeting our OEM or our custom set target cleanliness. So with that, we need to understand filtration. And when it comes to filters, we could get into a lengthy discussion about the construction of filters and, how they're built and what they do to increase, flow rates and capacities and all kinds of things. But at the end of the day, mostly what we need to understand is the media, the part in the middle, right? The big part of the filter, the most visible aspect of it, that's the part we need to understand. And really, media comes in 2 forms. The 2 primary types of media are what we would call cellulose, or some of us call paper. And the other one would be something that's usually referred to as glass, microglass, fiberglass, or just simply synthetic. And the big difference between these 2 types of medias is simply the thickness or coarseness of the filter fibers. Paper being much coarser, relatively speaking, than the synthetics. And when you wonder, well, what difference does it make to the filter? With a paper or a cellulose type fiber being these coarser fibers, we cannot get as high of a density of holes. We get a much larger restriction of flow. It's a bit more difficult to get small holes, small pores. It's not to say we can't. I've certainly seen, cellulose submicron filters, but just saying it's a bit more difficult, relatively speaking, compared to the synthetics. But we're dealing with a natural product, so the holes are very randomized and we don't have great control over this. Comparatively speaking, if you look at a synthetic filter and look at its finer fibers, well, then we get things working in our best direction here. So we get a higher density of holes, so more holes equals more capacity. We can do this with less restriction of flow and with smaller holes. So that's nice. We can get to a finer micron size a bit more easily, and we can maintain proper flow rates. But because this is an engineered product, we also have the ability to taper the holes, meaning one side of the media can have larger holes than the other side of the media. So as the oil goes through the media, the holes get tighter and tighter. Now, just to show you a comparison between these 2 types of fiber sizes, if you will, as just sort of a reference here, not a real image. But if you build both filters, a filter with cellulose and a filter with synthetic, and rate them both to the same micron. So the point is, I'm not trying to compare different particle sizes now. Saying these filters are rated for identical particle sizes, this is kind of what you would see is the big difference. A paper or a synthetic filter would have fewer holes and therefore would have lower capacity. A synthetic filter would have more holes and therefore would have a larger or longer, however you want to think of it, capacity. So the big difference between these 2 filter fiber sizes is essentially not necessarily the micron size that we're going to be able to rate these filters, but how long the filters will last, how much dirt they'll be able to trap before they go into bypass, other things like that. So one quick note here is these are only media types. There are also 2 different filter types, and basically they can either be called surface, or what many of us usually refer to as pleated, because that's exactly how they're constructed and what they visibly look like. versus the other styles called depth, or what many of us refer to as stacked, because again, that's how they're constructed and that's the visible aspect to them. But the big difference between a surface and a depth filter is that a surface filter is one piece of media and the oil flows through the surface of the media, which is why it's called the surface style of filter. But you get that one layer and one layer only that the oil passes through. With a depth filter, you essentially take many pieces of media and you stack them on top of each other, which is why we call them a stacked filter. But now the oil runs through that media lengthwise. So it goes through the depth of the media. Now, either filter can be made with either type of media. Those are options that are available. So it's not to say that all pleated filters are paper, or nor saying that all depth filters are synthetic. It could be either way. But predominantly what we're looking at is that with a surface filter, we typically use these in full flow applications, meaning where most of the oil is going to go through and is delivered to machine parts. Depth media type filtration is frequently reserved for what we would call a slipstream type filtration, or offline kidney loop dialysis. It goes by a bunch of different names, but this is where we take only a portion of the oil, flow it through the filters, and return it back into the reservoir of the tank. So we don't typically deliver oil from a depth filter into the machine parts directly, simply because the flow rates are significantly lower most of the time. I'm not saying there's not exceptions to this, but just if thinking overall usage, the main filters on any type of system typically are of the surface type, whereas when you see depth filters typically is in additional filtration systems. So like I said, slipstream type systems. Now, thinking that the surface type is the most common, one of the questions that I get is, how do you increase the capacity of a surface filter? Knowing it's only got one piece of media in it, how do you get more filter for your buck? Well, put more of the media in there, make that piece of paper bigger, and then start folding it up to get it in there, which is hence why we call them pleated filters, because we use pleats to tighten up how much media we can get inside the filter canister. Well, with this, we can increase the depth of the pleats and we can increase the density of the pleats. And if we're really creative, we can do a bit of both, and that's called a staggered pleat. And you can see that in the bottom left, and we're really able to maximize how much media we get in there. But at the end of the day, it still is just one layer. The oil still goes through the surface of that media. Just the larger surface area allows us to have a much higher capacity, longer life for that filter. Now, whether we're making it a pleated filter, surface type, or we're making it stacked, a depth type filter, at the end of the day, filters are rated to the same type of rating. And this goes again, whether it's paper or synthetic. When we rate a filter, we typically rate it using different terminology, and some of this may sound a bit familiar to you. If we're talking about a 5 micron filter as an example, I could rate it as a 5 micron nominal. I could rate it as a 5 micron absolute. However, I could also rate it using something called the beta ratio, which is hopefully something you already understand, but if not, wait a couple slides and we'll explain it. But the beta ratio is much more clear-cut than the terms nominal and absolute. When I say it's beta 75 as an example, I've got a good idea as to exactly how efficient that filter is per pass. So with these terms, knowing that all of them are relating to a 5 micron filter, you go, what's the difference? And essentially it breaks out like this. When I use the term nominal, I'm really saying that the filter could be as low as 50% efficient, which is actually terrible efficiency, up to but not including 98.7% efficiency. Sounds good, but it isn't. Absolute means it's 98.7% or better. And the problem with this is that there's probably, currently at least 4 grades of filters that can be considered absolute. So the term absolute is still a fairly wide range and doesn't necessarily mean it's the best filter out there. It could be essentially the 4th best filter out there. Whereas with beta ratings, you know exactly how good or not good these filters are. And that's why we need to understand what the beta ratio is. And looking at this, you go, how do you call it a beta ratio when it's only a single number? How is 75 a ratio? That is a great question to ask, because that is exactly what you need to understand to be able to convert the beta ratio to an efficiency and understand just how good it is. So with that, here's the beta ratio. The beta ratio is a number that we arrive at by doing what's called a multi-pass test. So what we do is we run the oil through the filter multiple times. That's how you get multiple passes. The beta ratio, though, refers to the efficiency per single pass. So that's why people refer to it as a single pass efficiency test. But it is run multiple times, and what we're measuring is how many particles go into the filter versus how many particles come out of the filter at a given size or larger. So again, sticking with our 5 micron as a value, if I was to tell you that the filter was rated at beta 5, 5 meaning the micron size, but beta 5, 20. 20 is the beta ratio. And like I said, it gets confusing to think, how is a single number a ratio? Always think of it this way. It's a ratio to 1. So it's 20 to 1 is what the beta ratio refers to. And so now you can accept the fact that it's a single number, because if it's always to 1, we don't need to say it's to 1. What we need to understand is to 1 what? So what does 20 to 1 mean? It means if 20 particles larger than 5 microns go into the filter, only 1 escapes. If we say it's a beta 75 filter, we mean 75 particles go in, 1 escapes per single pass. So that's why it's referred to as a single pass type efficiency. That's why it's a single number, because it's always to 1. And the number refers to how many particles larger than that micron size go in, assuming only 1 comes out of the same micron size or larger. So hopefully that's making a bit more sense, but look at it from a different perspective. What if I told you a filter was beta ratio of 1? What kind of filter would that be? Well, if it has a beta ratio of 1 particle going in and 1 particle coming out, it's not a filter, it's a hole. But if I told you it was a beta ratio of 2, when we appreciate that that is a 50% efficient filter, because if 2 go in and 1 comes out, 1 out of 2 are trapped, that's 50% efficiency. Now here's where the math might get a little bit tricky. People often get this wrong. If I told you it was a beta ratio of 3 though, how efficient is the filter, right? It's not 33% efficient. If the beta ratio is 3, remember 3 go in, but 1 comes out. So in essence, the filter trapped 2 out of 3. So that is now 66% efficient filter. And just to make sure we get this, let's try one more. Let's go up to a beta ratio of 4. Right? If 4 go in, 1 comes out, 3 out of 4 were trapped, so it's 75% efficiency. Right? If you need to see the calculation, sometimes working these out just in the air doesn't always help people. You need to see the calculation. I've reproduced it here, but basically take the beta ratio and subtract 1, because you always have to account for the 1 particle that escapes. Divide by your original beta ratio. So if I said it had a beta ratio of 4, well, that means 3. 3 were trapped because 1 did get out. And we have the original beta ratio of 4, so 3 divided by 4 is 75%. And my point is, if you look down this chart, beta ratio of 1 would be 0%, beta ratio of 2, on the other hand, would be 50%. That is the definition of a nominal filter. It's essentially the worst filter you can buy, the one with the lowest efficiency at that micron rating. If you go all the way up to beta 75, which was the other example I had shown you, beta 75 is where we define an absolute filter. So 75 or better is an absolute filter, but we have 75, we have 100, 200, and even 1000s as commonly available beta ratios. So the term's nominal is quite a wide range of efficiencies. The term absolute is also a fairly wide range of efficiencies. Only referring to it by a beta ratio can be considered definitive. That way you can calculate exactly how clean the oil should get after X number of passes. And that's an important thing to be able to do if time is not on your side and you need to clean the oil up quickly. You need to know how many passes on, at least an estimate that it's going to take to clean up your system. So beta ratio is a very important number. It is one that's quite key in selecting your filtration, but the focus should always, always, always come back to the micron size of the filter. And just to show you a quick example, this is a very old example, it's over 50 years old, but they started with 25 micron filtration, and it's just a nominal filter, nothing great. And the blue line represents the particle count, and you can see it started off quite high. The number that appears beside the line is how much of the particulate content was actually metallic, which of course means damage is occurring. Switching to a 5 micron filter, you can see the particle count drops significantly, but you also notice that the percentages went to 0 eventually. So the metallic content went away. Just to show you this wasn't a fluke because they simply changed the filter or something else happened to the system, they switched back to the 25 micron filter they've been using, and the particle count shot back up and the metallic content returned to 25%. So it's just further evidence to show us when selecting filtration, we worry about the micron rating first, and then we start thinking about the beta ratio, because there's no point getting a really high beta ratio if the micron size isn't going to be what we need it to be. So with that, thinking all the way back to step 1, we talked about what was the most important particle size to control, and the answer was clearance size. And one of the quotes I showed you was from an old lubrication engineering article that suggested that that micron size for a hydraulic system was somewhere in the neighborhood of 1 to 5 microns. I showed you the McPherson curve, which was for a particular bearing, and it showed that that was also somewhere in the neighborhood of about 5 microns. So just sticking with 5 microns is kind of a common number, not saying it's the definitive number for all systems, but it's one you come across frequently as a clearance size. Let's take a look at 5 micron filtration for a second. So imagine you've got yourself a filter salesman. He visits you and says, I'm willing to sell you some 5 micron filters. Now you think this is great, but he offers you a choice. He says, I can sell you the Beta 1000. It's the best I have, but it's also the most expensive I have. I can save you a bit of money if you switch to a 200. I can save you more money if you switch to 100. I can save you a lot of money if you switch to 75. So all 4 filters are rated to 5 microns or larger, but they all 4 come with a different beta ratio. How do you know which one to buy? Where is it important to save the money? So looking at it from an efficiency standpoint, if you did the beta ratio as an efficiency calculation, Beta 1000 is 99.9% efficient. So to drop it to a 200, as you can read, you're losing 0.4% efficiency. It does not sound like much. To drop it all the way to a Beta 100, you're only giving up 0.9% efficiency, which again does not sound like much. And to go to a 75 is really only 1.2% efficiency loss. And again, doesn't sound like much. However, from a different perspective, if I look at it and do the calculations on how many particles will be there after each pass, if I compare it to the Beta 1000, a 200 will let through a little more than 600 times as many particles. A 100 will be 10,000 times as many particles. And as you can read, a 75 works out to just over 30,000 times as many particles will escape these filters after just 4 passes. Now, both sets of math that I'm showing you here are in fact correct. There's no, trying to trick you here. How do you know which one to pay attention to? And that's where it gets tricky, trying to just simply use beta ratios or single pass efficiency numbers or doing any calculations as a quick way of determining which filter is the better filter, because it's easy to see which filter looks better. The question is, do I need it, right? Can I save money? If I'm filtering to the same micron rating, doesn't matter. So let's look at it from a different perspective. Let's see how I arrived at that lower set of numbers, and then you'll appreciate whether or not you should have a lot of faith in them. So how do you calculate how many particles are there after a single pass? Well, the calculation is fairly simple. You take your particle count and divide by the beta ratio. That'll tell you how many particles you now have after the filter per single pass. So if I had a particle count of 10,000 and a beta ratio of 100, 10,000 divided by 100 is 100. So there would then be 100 particles after the first pass. But if I want to calculate after 2 passes, I take the 100, divide by the beta ratio. So 100 divided by 100 is now 1. And I would know that I could get from 10,000 particles down to 1 particle in just 2 passes. So it's kind of showing you how the math works. But let me give you the example. Going back to those 4 filters we're trying to decide between, we're talking about 5 micron or larger particles. So let's assume we have 1 million particles upstream. How good are these filters? So there's the numbers in terms of taking 1 million divided by the beta ratio. There's the number you will get. So you can see the numbers of particles that would be present after 1 single pass. If I take those numbers in the bar graph over on the right and divide by the beta ratio a second time, I get this set of numbers which tell me how many particles there are after 2 passes. I can do it again for 3 passes, and I can do it again for 4 passes. So when I show you the 4 pass numbers here, can you say definitively that the 75 beta ratio, particle did in fact let through over 30,000 times as many particles as the Beta 1000 filter. I mean, it is true, that number is over 30,000 times higher. But what else are you noticing about these numbers? They're just decimals. Can you have a decimal of a particle? I don't know about you, but I'm thinking I either have one particle, or if I say I have less than one, pretty much saying I don't have any. It's kind of the same as saying zero. And this is my point. If you look at all four of these filters, all four filters were able to reduce a particle count of 1 million particles upstream to less than one. And to me, less than one is less than one. It's the same for all four filters. It doesn't matter how small that number gets as to be less than one. If it's less than one, there's none, there's not any, there's zero, however you want to phrase that. And that's the thing that I think helps you answer the question. When you're looking at buying filters, where do you focus your energies? Right? Micron rating first, but then when you look at the beta ratio, you now understand that really what it boils down to is, yes, the term we use is efficiency, but ultimately what we're going for is speed. And my logic is this: if you have one single pass, you are transferring lubricants from point A to point B. That's it. That's your one chance to clean up the lubricants, right? As you take it out of the drum, pump it into the machine, then yes, you will do that with the highest beta ratio filter you can find, right? But if you're going to continuously circulate the lubricant through a filter, my phrasing is, what you lack in efficiency, you will make up in passes. So you don't need to go to the highest beta ratio always. As long as you get that micron rating right, you will get the filtration that you need. Now, just to flip back to the numbers here for a second, so going all the way back to the first one, if I show you the particle count here after one pass, you see that none of the filters were able to do 1 million particles down to less than one in one pass. Now, after two passes, the Beta 1000 is really close. It did get it down to one, but to be truly less than one, you're gonna have to see three passes. And by the time I look at three passes, well, the Beta 200 also got it down to less than one particle in three passes. So if you're considering, to ultimately get it down from 1 million to less than one, if those were in fact your numbers, that really either the 1000 or the 200 would both do them in three passes. And then, like I said, if you look at the numbers, after one more pass, then the other two do it as well. So it's all about speed, all about time. How much time do you have? How many passes do you want to circulate your oil before you achieve that particle count? Just to show it to you from another perspective here, referring back to the SAE technical paper I quoted in step one, it said that the critical particle size to control was between 2 and 22 microns because that was for an automotive application. What they did is a further study, and in this, they revealed the data that said compared to a 40 micron filter, if you filtered engine oil with a 30 micron filter, you reduced the wear by half. Pretty significant. If you went to a 15 micron filter, there's a further 70% reduction. There's actually more numbers to this, which I'll show you in a second, but the point is, right, it's all about the micron rating because an engine oil system is continuously circulating, so the beta ratio is not terribly important as long as we've got the micron rating for the filter. Now, 40 micron filter is basically filtering visible particulates, so that's not very good. But as we get finer and finer, we get longer and longer engine life or less and less wear. And that's where you see the second quote where it says the micron rating of the filter as established by the single pass efficiency type test, which is a big mouthful to say beta ratio. But as long as you've confirmed through testing that it does achieve a certain beta rating at a certain micron size, it does an excellent job at showing us the ability to remove those abrasive particles in the engine, which lead to wear. So just to give you the full set of data here and give it to you graphically, if we assume that a 40 micron filter gives us an engine life cycle of 1, here's the other data showing you how the engine life cycle can be increased with finer and finer micron ratings. Now, at some point, you have to take this data with a grain of salt and go, does it matter? And it's one of my favorite questions when I have a large live group is to poll the audience and ask them what their jobs are. And this is just kind of an interesting setup because when you find people who work right in the field, who handle lubricants on a day-to-day basis, compared to people who are more management type roles who maybe just sit in the office all day, the next question reveals a stark difference. And I'm assuming there's a few reasons for this. But my next question is, how many miles do you have on your vehicle that you currently drive? And they're often, not always, but often, is a stark difference, and that I will get 200, 300,000 miles as answers from the people who operate equipment and who work on them and lubricate them and all these kinds of things. And I'll often get answers of less than 100,000 miles for the management type people. Now, there may be multiple reasons. One of the reasons may simply be management earns a higher rate of pay and they just choose to buy vehicles more often. That's fair. Can't say that doesn't happen. But more what I find it is that people who are involved in reliability in a practical sense take good care of their vehicles and they last a long time. But where I'm going with this isn't to point out the class differences between workers. It's because when I get some of these answers that are 200,000 and 300,000 miles, sometimes even higher, my next question is really telling, because I ask people this. I single them out of the audience and say to them, all right, you with the 300,000, so have you ever worn out an engine? And almost without fail, no one will answer yes to that question. Now, on occasion, I will get a yes, and then I'll clarify with them. I'll say, did the engine wear out or did something break? And more times than not, something broke. Something fatigued to the point where it cracked. Something may have seized because of a lack of lubrication. But I've really never had anybody honestly be able to tell me, yes, I have worn out an engine. So when you see a graph like the one I'm showing you here that talks about reducing engine wear, I mean, that sounds great, but on the other hand, do you actually need that? Have you ever worn out an engine? Have you ever had enough wear that it caused an operational issue? Not many of us, right? So to that end, I wouldn't be looking at 5-micron filtration as a goal for my engine to get an 8 times life, because I really don't need my engine to last 8 times longer than it already does. I've never worn one out yet. The current vehicle I drive right now has got 256,000 on it, and I think it's broken in at this point. I'm quite happy. So take this set of numbers here with a grain of salt. Like I said, understand that we don't need to go to the nth degree on the micron rating and push for the longest life possible, because it's just not that practical, not that required. However, one group that did look at this data and come up with one of their own numbers to focus on picked the 10 micron value of 4 times life extension. That they felt was reasonable. You could market that seemed practical. Now, full disclosure, before I show you the data, this is coming from Purelator. So I like to mention that because what Purelator did was they compared aftermarket brands of filters, which of course Purelator is one of the manufacturers of, and tried to show us who makes the best aftermarket filter. So knowing the study comes from Purelator, you can take a pretty good guess as to what's going to be the top answer. And yeah, it comes out to be Purelator. So it's kind of funny because people often ask me if they know my work history. Knowing that about 15, 20 years ago, I worked for a filter company as a research scientist, they'll ask, who makes the best filter? And my answer to that is always this. It's not who makes it, it's who is it's made for. And the point is that what you're looking at here are all aftermarket filters. And these are all built for the aftermarket world. So they are what I would consider to be aftermarket efficiency. Now, picking on Fram there for a second, the second choice noun, that filter, if you were to look up the full specs on the filter, they're going to tell you it's a 10 micron nominal. So that means at 10 microns beta ratio of 2, which closely matches Purelator's data here. And then they're going to tell you it's a 40 micron absolute, right? Filters can be dual rated, both nominal and absolute. Nominal is always the smaller size, absolute is always the larger micron size. But they're going to tell you it's a 10 micron nominal, 2 micron absolute, or sorry, 40 micron absolute, getting ahead of myself here. So knowing this a 10 micron nominal, I was curious what filter quality I had as my OEM filter for my vehicle. Turns out it was a 10 micron absolute, and it was a 2 micron nominal. So you could say that by comparing it to a Fram, I was either comparing a 2 micron nominal to a 10 micron nominal, or I was comparing a 10 micron absolute with a 40 micron absolute, or really the easiest comparison is to keep the micron ratings the same and say my OEM filter is a 10 micron absolute, whereas the aftermarket is a 10 micron nominal. Well, one day I was doing a training class and some guys approached me when they found out what kind of car I drove and said we had a chat, cars, because they're a couple of gearheads. And, I said to them, honestly, I'm not that much of one myself. But they did ask me questions. What kind of oil did I use? What kind of filter did I use? So when we talked about filters, they told me right away, I said, oh, you shouldn't use an OEM filter. They told me about this other aftermarket brand that I should try. And, I just politely dismissed them. And that I thought was the end of the discussion. Well, the next day in class, they show up with one. First one's free, right? That's always the logic. So they hand this filter to me. I politely take it. Later that night in my hotel room, I'm looking at this filter going, what am I going to do with this thing? I don't really want to use it. So I was curious. So knowing the resources I have, I was able to look up who actually built the filter. And it was a company called Intertech. So I looked at the specifications for the filter, and lo and behold, it was the same 10 micron absolute, 2 micron nominal that my OEM filter was. It just was a little bit pricier. And they told me specifically not to buy the local, North American brand. They told me to buy the Japanese version, that the imports were better. So I looked at the import version, it was the same answer. So I'm finding that there's 3 filters out there that all have the same rating. Now, 2 of them are made by Intertech. My OEM one, I know, was not made by Intertech. But I never really paid attention to where it was made until I ordered a case of them one day. And rather than being individually shrink wrapped like they normally came shipped to me, they just sent me the whole box. And the box, in inch-high letters across the bottom, proudly stated, made in Oakville, Ontario. It does not take much of a Google search to figure out who's got a factory in Oakville, Ontario, and I'll tell you this, it ain't Intertech, it's Fram. So when people say Fram doesn't build good filters, I'm like, no, Fram builds decent filters. So does Baldwin, so does Paul, so does Wix, so does many, many companies build decent filters. Question is, who do they build them for? When they're built for an OEM to an OEM spec, they're generally a lot better than when they're built as an aftermarket spec for the stores to sell. So don't always go looking for the brand is what I'm getting at. You want to look for the micron rating, and more importantly, you want to look at the beta ratio as a confirmation has been tested to that micron rating. And sadly, with automotive filters, you're not going to find it. It's not printed on the packaging, it's not printed on the boxes. Now, there are ways to look them up online. You can always phone a distributor and ask the questions, but ultimately my short answer is this: buy OEM. So this raises a different question though, when people start thinking about industrial oil filters and they wonder, is there such a thing as too good of a filter? And sort of my long story short on this one is, as Heather introduced me, I am the editor of TLT magazine, which primarily means I get to write a column every month about 700 words, say whatever I like. And there was one topic I knew I couldn't address in 700 words, so I had dinner with one of the other writers a few years back. His name's Neil Cantor, and I pitched him an idea. And I said, look, Neil, you always interview lubricant suppliers, base stock suppliers, additive suppliers. You always interview these people in your articles. I said, I know you have the right contacts to answer this question. I'll give you all my filter contacts, and you can ask them the same question, see if we can get consensus, and let's publish an article about this. And my question was, can filtration be too good? Can filtration actually remove additives? And to keep the story as short as possible, he created a list of 16 people to interview, asked them a series of questions. When he got to that critical question, 10 of them backed out of the article. So that wasn't the good news, but 6 did agree to it, 5 of which on condition of anonymity, meaning we couldn't publish their company names, nor could we publish their names. The 6th guy, he was willing to go on the record totally with his name and company behind him, but we couldn't out him that way. So if you do read the article, it'll just say, filter supplier 1, 2, and 3, additive supplier, lubricant supplier, base stock supplier. It doesn't tell you who they are, but I assure you it's big names. Anyways, these 6 guys all had to come to an agreement with the answer to the question, submit it to Neil. Neil wrote up the article. When he's done, he sends it back to the people he interviewed so that they can review it. So this isn't quite a peer-reviewed paper, but it did mean that everybody got to see what everybody else said, because what if you're the one guy out of 6 who disagrees with the rest of them? You either need to be really sure you disagree, or you maybe want to change your answer. So my point being, all 6 agreed to the following statements I'm about to show you. So the first one here, and now this is my underlining, okay, so this is not how it appeared in the article, but the first one says filtration studies on new and used lubricants with a variety of base stocks, so this is not unique to just like say mineral or PAO, showed that no additives were removed even after hundreds of passes. And just to save you reading all 7 pages of the article, they used 1.2 and 3 micron filters for these studies. So we got some pretty decent confirmation that no, you cannot over filter a lubricant, you cannot strip out the additives directly with a filter. Now saying that, the one guy who's willing to go on record, he is a friend of mine, and he goes, but Evan, you can remove used additives. And I said to him, I don't like the word used. Used just means not new. I said, you can remove a spent additive. So there's my 1-word contribution to the whole article. I changed the word used to spent. That's my other job as editor. But the point is, if you had, say, a dispersant additive in your oil and you had soot particles in it because it was an engine oil, and the dispersant bonds with the soot, if you filter out the soot, did you in fact filter out the dispersant too? Well, technically speaking, you did. But can you say definitively that a filter removes dispersant additive? No, you can't. And do you really care that it did? Because I mean, once it's bonded with the soot, it's already done its job. It's keeping the soot from agglomerating with other soot particles. So what do you care if the additive is there or not? It can't bond to another one. So I'm just trying to, every way, shape, form I can, just warn you and help you understand that when it comes to filtration, a lot of times people, when they start looking at that target cleanliness we set in step 1, decide that they're willing to work towards it, but not necessarily really aggressively attack it. And therefore they'll hold off on too fine of a micron rating because they are worried about removing additives. Additives are in the nanometer scale. They're submicron. They're 1/1000 of a micron, most additives. You're not going to remove them with filtration. So with that, pick a micron rating that appeals to your clearance range, that will get you your target cleanliness. Pick your beta ratio based on how much time you want to take. If you've got full flow, constantly recirculating through a filter, like I said, you can go with a low beta ratio. If you only get 1 or 2 shots at this, you're just filtering, before it goes into the machine, you're going to want a higher beta ratio. So hopefully with that, you got your answers to all your filtration questions. Just as a quick overview here, just due to the time factor here, I'm at the end, so I will be happy to take any questions that we have now. Turn it back over to Heather and see if we did get any in the chat.
And yes, we did get a number of questions, and one of them was, does fine filtration deplete the additives in the oil, which you actually just ended the presentation with that one. So
good.
There. One of the first questions was, is a bypass filter a depth filter?
Bypass just means, like I said, taking a portion of the oil's flow and sending it through any type of filter, could be surface or depth, and returning it to the system, not delivering it straight to the lubricated components. So no, bypass does not imply that it is depth, but I would say the other way around. Usually when we do use a depth filter, it is in a bypass setup, but no, you can have bypass filtration with a surface pleated type filter.
Great. And then what is the difference between beta ratio and NAS or NAS value?
NAS is a cleanliness target that's similar to ISO codes, similar but still a bit different. But just referring to number of particles per volume of fluid, instead of being per 1 mil like ISO is, NAS is per 100 mils. And instead of having ISO codes or NAS classes, so really just a different numbering system. The biggest difference is that the way NAS is done is what we call differential. The ranges are defined 5 to 15 microns, 15 to 25, so on and so forth. Whereas ISO is what you call a cumulative count, and it is 4 and up, 6 and up, 14 and up. So they don't cross compare, but they're of the same, type. They're, like I said, the cleanliness goal. But no, they've got nothing to do with filter ratings from that perspective, if that's what the question was asking. I hope I understood it correctly.
It sounds like you did. I believe you did answer the question there. And our next one, do depth filters always have an advantage over full flow filters in one pass?
Yes, they're far more efficient in a single pass. If we were talking about rated to the same micron, a depth filter would take out significantly more particulate than a surface type filter, just because of the nature of the design, for sure. Yeah.
Perfect. And we have a couple more here. So how is pressure drop across the filter and how long the filter can be used affected by how small a particle size that is being filtered out?
Well, there's a slight relationship to that. Obviously, the smaller the micron rating, the more of a restriction you could expect. However, like I said, we can balance that by making the pleats deeper and more density to the pleats to increase the surface area, so that even as those holes, even though they're smaller, we just have simply more of them. So the overall, if you want to think of it as surface area of flow through the filter, we can balance that to a point when it comes to filter design. So you don't necessarily have to sacrifice a restriction of flow or a higher differential pressure or anything like that. But understandably, it will play a role. Typically at some point, if you want to upgrade your filters by going to a smaller micron size, right? That's where the word upgrade gets a bit, counterintuitive.
A bit ironic.
At some point, though, typically you do have to start looking at a larger overall filter dimension. You have to change your filter housing size to accommodate a bigger size of filter so that it can have the correct surface area to maintain flow. So there is a relationship. It's not to say that immediately if you took a 10 micron filter and looked at a 5 micron filter, that a 5 micron filter has half or any variation of restriction of flow. I could build a 5 micron filter in a way that would have the exact same flow a 10 micron filter could. It's when I start going down to 3 microns, 1.2 microns that I can't maintain that level of construction to get you the same flow rate with the same low differential pressure. So there is a relationship, but it's not to say it's like 1-to-1 or that it's a linear relationship according to micron size. It will vary as you get to the smaller ones, and it will become only really important when we go down to about 1 micron or less. That's when flow really gets restricted.
I see. And we are 1 minute past the hour, so I'll leave it at one last question. For anyone that does have questions that we weren't able to answer, if those are in the question area of GoToWebinar, Evan will be emailing you after the fact later today to answer those. And if you think of a question later on today, Evan's contact information is on the slide right there, so please feel free to reach out to him at any time. And with that, our last question is, do you have to consider the type of contaminants entering the system when choosing between cellulose and synthetic or surface and depth filters, specifically when considering water?
Well, yeah, I was going to say really only water, because most of the paper cellulose type medias are not very resistant to the water, and water can absorb upon the surfaces, leading to them collapsing or tearing. So water is a consideration, but if you're concerned about filtering out, hard particulate versus softer particulate from process degradation and whatnot, depth filters do a much better job at removing the soft particulate from degradation mechanisms than any type of surface construction will. Cellulose filters are known to do a bit better job than the synthetic or microglass. So when you're trying to remove among the smallest particles, typically we go to depth, and typically we stay with cellulose. It's not to say always, but typically we do. If you're only removing hard particulate, typically you go with a synthetic filter, and you stick with your pleated design, unless there's water. And if there's water, we have to stay with synthetics because they can tolerate water. They don't collapse. They don't absorb it. There's always options too that we can treat the material. There's ways to make them hydrophilic so the media actually absorbs it. So we do this with like polymeric synthetics and stuff like that. So there is some consideration to answer that question with, yes, what are we trying to remove? And yeah, we do stay away from the cellulose. If we know it's a wet system, if we know we have high levels of humidity at all times, it's going to lead to shorter filter life. So to maximize it, we would go to synthetic. But like I said, depth is usually reserved for trying to remove the softer style of contaminants.
Right, perfect. Well, Evan, thank you very much for your time today, and thank you to our attendees. You'll be receiving a recording of this webinar later today. And if you have any questions, please always feel free to reach out. Evan, thank you so much.
Thank you.